Uh, Hi. I want to talk about just go back to the ideal op-amp model for a moment, okay? And the assumptions that we have in an ideal op-amp can be encapsulated by kind of a model for our op-amp, a mathematical or a electrical model for the op-amp, and that model is shown on the screen here. So um, look at this with me. So we have two voltages, V1 and V2, applied to the non-inverting and the inverting terminals of the op-amp, and the difference of the two voltages is Vd. Now, by some internal process, the op-amp takes this Vd, multiplies it with the differential gain, and gives that voltage at the output, right? So that's what happens in an op-amp, right? The op-amp output is only dependent on Vd, and AD is very very high, and let's assume that it's nearing infinity, and in that case this looks like an ideal op amp. Notice also, what's the current going into the non-inverting terminal? It's going to be zero. Why is it going to be zero? Because there is no connection here for the current to flow. This is just an open circuit here, and that kind of models the zero current requirement of the ideal op amp. What is How is this voltage dependent on the current that is flowing out of the op amp? It is not dependent, right? This is a voltage source and it's not dependent on the current. How much ever current can be supplied by the op amp to the load, and that kind of encapsulates the third criteria. So all the three criteria are kind of modeled in this diagram. Now let's see how the op-amp behavior then deviates from this ideal behavior. Okay, so one way in which it deviates is the fact that the deviation can be modeled by putting a resistance here in the path of the output, right? And let's call this resistance RO. Now think about what happens. Now the current that is flowing out of the output terminal, let's call it I out. Okay, as I out increases, what happens to the voltage drop across this RO? As this current I out keeps increasing, as it becomes more and more, okay, so this current becomes more and more, what happens to the voltage drop across this resistance? The voltage drop increases, right? Because the voltage drop is given by I out times RO, and that increases. What does that mean for the output voltage here? Okay, so if you want to write the equation for V out is going to be AD times VD. Okay, let me use another color, sorry. So V out is going to be equal to be AD times VD minus I out times RO. So as this I out increases, what happens to V out? V out decreases, right? So your op amp cannot supply infinite amount of current, because if I out becomes large enough, V out becomes zero. So as the current keeps increasing, the output of the op amp keeps reducing. Okay, and that is the consequence of the output resistance of the op amp. So all op amps have a finite output resistance, because of which op amps cannot supply an infinite amount of current to the load. There is a limit. Okay, okay, so that's one thing that we can change here. Another thing that we can change here is we can put impedance between the input terminals of the op amp. Now what would happen if you do that? If I put, let's say, a resistance R in between the non-inverting and the inverting terminal, what is the current going to be which is going in inside the op amp? So this current I in, what happens to that current? That current is no longer finite. Sorry, zero. It's a finite current, right? So I in is given by Vd over Rn. and that is equal to, so I can write it as I in plus, and this is the same as I in minus. Okay, so we can write it as I in minus, and because of the direction I can write it as minus of that, right? So in an ideal op amp you have no current flowing into the op amp input terminals, but in a real op amp some current flows. Now in an ideal op amp, the op amp can supply as much current as the load needs without any change in the output. But in a real op amp, the op amp cannot supply infinite amount of current. There is a limit, and after that limit, the voltage starts going down as the current increases.